Good morning and welcome to this, the 27th lecture of the course Water Resource Systems, Modeling Techniques and Analysis. Over the last few lectures, we have been discussing about the reservoir operation problems, reservoir design problems and so on in a deterministic framework, in the sense that the sequence of inflows is known and all the hydrologic variables that influence the decisions are supposed to be known with certainty. And this type of framework is called as a deterministic framework. And in that deterministic framework, we have made several decisions, or we have built models to make decisions on what is the minimum reservoir capacity that you need to provide to meet a certain sequence of demands, or how do you operate the system optimally to meet certain objectives, to maximize, let us say, the hydropower generated, or to maximize the returns that you expect and so on. Even in the case where we considered the stationary policy or the steady state policy using the dynamic programming, the sequence of inflows was constant, was held constant, in the sense that the same sequence keeps repeating year after year if you have annual flows. And if you have a larger sequence of flows that you would like to make use in the decisions, let us say 30 years of sequence you want to make the use of that particular sequence in making the decisions, you may build the models over those 30 years hydrologic variables, including the stream flows and so on. But the 30-year sequence still remains the same after 30 years, in the sense that we assume that essentially the same 30-year sequence keeps on repeating after the 30-year windows. Now, these are called as deterministic problems. So, specifically in the last lecture, we dealt with the hydropower generation problem, and in that we dealt with both the run of the river system as well as the hydropower generation with reservoir systems. So, in the reservoir systems, recall what we did. You have a penstock and then you have the turbines located somewhere here. So, this defines the head available for power generation. This is the water level, and if you have a tail water level, and let us say this is H2 as we used in the last class. So, this is the total head corresponding to the storage, and then you have the tail water level, that is H2. So, the net head we define as H1 minus H2. So, this is the net head available for power generation after accounting for losses and so on. As we saw in the previous class, to generate a given power P associated with the head, net head HT and the overall efficiency eta, we obtain RT in terms of million cubic meters. This is the release to be made from the reservoir in million cubic meters, and this is the expression where P is in megawatts, HT is in meters, and this we are talking about for a monthly time period. You can refer to the last lecture. This is the expression that we obtained. And then we introduced a iterative procedure, because the net head depends, or the total head depends on the storage. So, HT when we are talking about, which is the net head during the time period T, and therefore, it will depend on the storage at the beginning of the time period T, ST, as well as storage at the end of the time period T plus 1 during time period T. Now, if you look at the continuity relationship here, the ST plus 1 is not known. When we are doing simulation from one time period to time period, this is not known, and the head here HT, and therefore, the RT here, because RT depends on HT, and also ET, which depends on the area of water spread, which is changing from the beginning of the time period to end of the time period, because it depends on the storage, as you can see here. All of these need to be determined simultaneously, and we introduced a iterative procedure for obtaining HT, RT, ET and ST plus 1, all of them simultaneously in the simulation procedure that we saw last time. In addition, we introduced the concept of primary as well as secondary power. Recall that we also defined the firm power and the secondary power, both in the case of run of the river system as well as in the case of reservoir systems. So, the firm power is the power that is available with 100% reliability. This is in fact the minimum power that can be generated for a given hydrology and at a particular site with the turbine capacity fixed and so on. So, that is the minimum power that can be produced. The secondary power is available with 50% reliability. That means, at least 50% of the time the power generated will be greater than or equal to that particular power. The primary power is the power that you would like to generate all through the year to the best extent possible. That is, you will set a target power and then you would like to maintain that particular power all through the year. In the example that we studied in the previous lecture, we considered the primary power to be 73.5 megawatts. So, you would like to produce 73.5 megawatts constantly all through the year, whenever it is possible. And when it is not possible, you will make the complete release. When it is not possible because of the water availability constraint, you will make the complete release and then produce whatever best power that you can produce, which will be less than the primary power. Then the secondary power will correspond to the spills that are occurring. That means, the reservoir has reached its capacity and still you have excess water that is going out as spill. In certain situations, you can use the spill water also for producing the power. At least in the planning stages, you would like to see whether you can actually utilize the spill at the maximum head that is possible, corresponding to the capacity of the reservoir, and produce the additional power. So, you have the concept of primary power and additional power, concept of firm power and secondary power. Now, there we will complete the deterministic modeling procedures. Now, we will see an important concept in water resource systems, which is that dealing with uncertainties associated with the hydrologic variables, primarily the hydrologic variables. There are also other uncertainties associated. Those things are typically covered in the advanced water resource systems courses. As I have been mentioning, in all the procedures that we are dealing with, the hydrologic variables, primarily you look at the evapotranspiration or evaporation, the stream flows. Now, these are the primary hydrologic variables that we use in making decisions. All these hydrologic variables are burdened with uncertainties associated with natural processes. For example, you are looking at the stream flow at a particular location. Let us say you are looking at a catchment and then you have the reservoir at this point. This is a reservoir and it has its catchment, and the stream flow here is governed by, this is a stream flow, is governed by the rainfall that is occurring in the catchment, and the rainfall is typically associated with randomness. Or I will say rainfall is a random variable, and because rainfall is random variable, the stream flow which is dependent on the rainfall also becomes random variable, and therefore, there is an uncertainty associated with the stream flow process. Similarly, if you are looking at the evaporation at this point, or let us say you are taking the water and then you are applying for irrigation, this is the irrigation district or irrigation area. Now, in this there is a evapotranspiration taking place. Now, evapotranspiration depends on straight away first the temperature, which is a random variable, and then it depends on the soil moisture, which depends on the rainfall and so on. So, the evapotranspiration becomes random, and evapotranspiration determines the demand that has to be met from the reservoir from time period to time period. So, most of the hydrologic variables that we deal with in water resource systems are burdened with uncertainties, and the first level of uncertainty that we talk about is the uncertainty associated with randomness of the hydrologic variables. So, when you are making decisions for the future, you need to account for the uncertainties associated with all the hydrologic processes. For example, you were in our earlier classes, we determined the reservoir storage for a given sequence of inflows, assuming that the same sequence will repeat year after year. It is well known that the same sequence will not repeat year after year. However, there may be certain probabilistic characteristics of the stream flow sequence that may be preserved. For example, the probability distribution may be preserved in the future. So, when you are making decisions based on the historical data, you will want to consider the uncertainties in terms of the probability distributions of these various variables. So, we must have methodologies by which we make decisions in the face of these uncertainties, by incorporating the uncertainty and not by ignoring the uncertainty. In the case of deterministic optimization, deterministic procedures that we developed earlier, we simply ignore the uncertainty, but uncertainty is a major component in any water resource systems, and therefore, in any water resource system, and therefore, we must have methodologies through which we address. So, now onwards, we will now move on to methodologies incorporating the uncertainties. So, what we will be now talking about is the reservoir systems with random inflows. In this course, primarily we will consider uncertainties only associated with inflows, but as I mentioned, the uncertainties are associated with most of the hydrologic variables that we deal with. Evapotranspiration is uncertain, evaporation is a random variable, the soil moisture is a random variable, the groundwater levels are random, the groundwater flow itself is random, and so on. So, there are uncertainties associated with virtually any hydrologic variable that we deal with in water resource systems. However, the primary variable which governs most of our decisions is in fact the inflow to the reservoir. So, we will start introducing the concepts of uncertainties with respect to the inflows, and specifically in this course we will deal with reservoir systems with random inflows. So, the uncertainty in hydrologic variables leads us to the methods that we are going to develop now. We dealt with optimization techniques to determine the size of the reservoir earlier, as well as to determine the operating policy of the reservoir, in which case the sequence of stream flows was held constant or was treated as deterministic. Now, because of the uncertainties associated with the stream flows now or the inflows, we start modifying the procedures that we have developed earlier for deterministic sequences to incorporate in some sense the variations that are likely to occur in the stream flows or in the inflows. There are two primary optimization techniques that we deal with in such a situation. One is called as the implicit stochastic optimization and the other one is the explicit stochastic optimization. Let me explain what we mean by that. So, there are two ways in which we deal with the uncertainties in optimization. Let us say you have the optimization model here. in the implicit stochastic optimization called denoted as ISO, implicit stochastic optimization, the optimization model itself remains deterministic. But the sequences that are that we are using to run this optimization model, let us say you have the input sequence. These input sequences we will run for several such sequences. That is, we take one inflow sequence, let us say you have 30 years of flows, and then you run this optimization model for that particular sequence, you get some output and change the input sequence. How do we change the input sequence, or how we generate several sequences of flows and so on, is slightly beyond this particular lecture, but in subsequent classes I will discuss that also. So, there are ways of generating several sequences of inputs, inflows to the reservoir. So, run this optimization model, which is essentially the deterministic optimization, a deterministic optimization model for several sequences of inflows, and therefore, we are considering the randomness associated with the stream flows outside of the optimization model, and therefore, it is a implicit stochastic optimization. Associated with each sequence of inflow input, you get one sequence of output. Let us say you are talking about reservoir operating policy. You used yearly flows for that. So, 1 year flows you used and then got the operating policy. You change the sequence to make sure that the uncertainties associated with the inflows are incorporated. You change the sequence, get another year flows and then get another output, and so on. Or if you had a 30-year sequence, run this optimization model, which remains constant, which remains in a deterministic framework. You run this for several sequences, and therefore, you will get several sequences of outputs, and then you can do some analysis on the outputs that you produce to account for the uncertainties here. So, this is the way of addressing the uncertainty implicitly. So, this is implicit stochastic optimization. But a more compact and more elegant mathematically is the explicit stochastic optimization. Or the ESO. Now, in explicit stochastic optimization, the optimization model itself has the probability distributions or the probability information or the uncertainty information associated with the input variables inbuilt into it. So, the explicit stochastic optimization considers the probability information probability distributions. Let us say, I will define what are all these things presently. Distributions explicit. So, the probability model that we had earlier is itself a stochastic optimization model. And therefore, all the uncertainty information associated with the flows and all other hydrologic variables has been already incorporated in the model itself. You run the model only once and you get the output with the associated uncertainties defined. Output also will have its own distribution. So, you run the stochastic optimization model only once, unlike the implicit stochastic optimization model, which you need to make in which you need to make several runs of the optimization model, each associated with one sequence of inputs. So, that is the primary difference. So, in the implicit stochastic optimization model, the model remains deterministic. You run the model with several sequences of inputs, all of which together address the uncertainties in the input, and therefore, associated with each of these sequence you get one output sequence, and therefore, you will get several sequences of outputs, and then you do the analysis on the outputs to get the decisions incorporating the uncertainties. Therefore, the optimization model is run several times, whereas in the explicit stochastic optimization model, the optimization model itself considers the probability distributions, and therefore, the optimization model is stochastic optimization model. You run it only once, and then you get the associated decisions output with the uncertainty. So, you run it only once. Input actually it is specified in terms of the probability distributions and so on, we will see that later. So, these are the two primary classes of the stochastic optimization. Now, in explicit optimization, we have two major techniques that we will be dealing with. One is the chance constrained linear programming. This is denoted as CCLP, chance constrained linear programming. Another is stochastic dynamic programming, SDP. The implicit stochastic optimization, I repeat, does not need any special treatment now, because the optimization problem itself remains the same as what we covered earlier in the deterministic optimization, except that you run the optimization model with several sequences. How to generate the several sequences and so on, perhaps we will cover later, or you can refer to other courses on stochastic hydrology to see how you generate several sequences. So, what we will do now is that we will begin with some basic concepts of probability. I will quickly review the probability theory, so that the students will get used to the concepts that we will be using subsequently. I would encourage you to look at the NPTEL course on stochastic hydrology for this basic concepts of hydrology, basic concepts of probability theory. So, I will write here this, you can refer to NPTEL course on stochastic hydrology. All the basic concepts have been covered in that particular course, but we will quickly review what we need for this particular course. So, there is an important concept of a random variable. Let us say you look at the inflows. Inflows are generated by precipitation typically, along with the other processes that take place in the catchment, such as evaporation, such as depression storage. There may be also infiltration that is taking place, there is an interception that is taking place before the runoff starts and so on. So, there are a large number of hydrologic processes, there are a large number of natural processes that affect the stream flow, generation of stream flow, and all of these vary randomly, and that brings us to the concept of a random variable. You look at a Newtonian type of equation where you are saying let us say S is equal to u t plus half a t square. You specify the u, which is the initial velocity and the acceleration for a given time. The S, which is the distance covered, will remain always the same irrespective of at which place you apply this equation, at what time you apply this equation and so on. Now, these are deterministic forms of models, whereas you look at the rainfall runoff process itself. The rainfall runoff process, for the same rainfall in a catchment, you are modeling let us say the stream flow, you are measuring the stream flow at this point. For the same rainfall in the catchment, you may get different runoff during different times, and if you have the same area of catchment at different location, you will get a different runoff and so on. So, the rainfall runoff relationship is a random relationship, is a stochastic type of relationship, where there is a uncertainty associated with runoff associated with a given amount of rainfall. So, the concept of random variable is it is that particular variable intuitively, mathematical definitions and so on, you can refer to the stochastic hydrology course. So, intuitively what we mean by a random variable, it is that particular variable whose value cannot be predicted or whose value cannot be known in advance until it actually takes the value. What I mean by that is, again compare this with Newtonian type of models, S is equal to ut plus half at square, the simplest one, where you specify u, you specify t, specify a, you can always get S. You can know S a priori, whereas the random variables, you are looking at the runoff at a particular location. Even if you specify rainfall, you will not be able to know certainly that this should be the rainfall, this will be the runoff precisely until it actually takes on the value. So, intuitively the random variables are those variables whose value cannot be known in advance until it actually whose value cannot be known until the value actually occurs. This is the intuitive definition. Of course, there is a mathematical and more formal definitions of random variables and so on. You can refer to the stochastic hydrology course. Now, with this primary definition, then we move on to slight mathematical treatment of this, for which we define the probability distributions. So, there is a concept of discrete random variable and continuous random variables. Now, the discrete random variables are those which assume only discrete values. For example, the number of rainy days is a discrete random variable. It can only take on values such as 0, 1, 2, 3, etc. It cannot assume a value of 0.5, for example. If it rains, it is a rainy day. If it does not rain, it is not a rainy day. So, that is one of the examples. So, if a random variable takes on only discrete values, then it is called as a discrete random variable. Now, associated with discrete random variables, then we have the concept of probability mass function. So, let us say x is your random variable and it can assume x1, x2, x3, etc., xn. Associated with each of these events, that is probability of x being equal to x1, associated with the event x is equal to x1, there is a probability, associated with the event x is equal to x2, there is a probability, and so on. And this defines what is called as a probability mass function for a discrete random variable. These probabilities are non-negative, and the sum of all the probabilities over all the values that it can assume must be equal to 1. Which means that exactly one of these values is sure to occur. Therefore, probability of x is equal to x1 plus probability of x is equal to x2 plus probability of x is equal to x3, etc., must be equal to 1. Then we have the concept of cumulative distribution function. It simply gives the cumulative probabilities. For example, this is probability of x is equal to x1, probability of x is equal to x2. So, this value here is probability of x is equal to x1 plus probability of x is equal to x2. So, this is a cumulative probability. Similarly, this value will give probability of x1 plus probability of x2 plus probability of x3 and so on. So, this is probability of x 1 plus probability of x 2 plus etcetera probability of x n, and the last value that you get here in the case of discrete distributions will be equal to 1. So, this is the concept of cumulative distribution function, and therefore, it is denoted as f of x, capital F of x is equal to summation for over all x I less than or equal to x for this particular value of x, probability of x I. What I mean by that is, let us say that you want probability of x being less than or equal to a particular value x 4. You sum all the probabilities up to x 4, and that is what you get as probability of x being less than or equal to x 4, and this is what is that particular value. In the case of discrete random variables, the mass function that we have thus defined gives the probabilities of discrete events. We now go to the continuous random variables, and one more important point that you must remember is that we denote by capital letters the random variables themselves, and by small letters the value that the random variable takes. So, for example, x, y, z, etcetera, like this, capital letters denote the random variable, and the associated small letters x, y, z, etcetera, these denote the value of the random variable. For example, x may be stream flow, y may be rainfall, and z may be evapotranspiration, etcetera. Then we can say x is less than or equal to x, that is stream flow is less than or equal to a given value of x. We may write x is less than or equal to 30. So, this small x denotes the value that the random variable takes. So, this is one convention that we use. Just keep this in mind when we are covering the probability models. Okay, then we move on to the continuous random variables. Discrete random variables take on only discrete values 0, 1, 2, 3, etcetera. The continuous random variables, on the other hand, take on a value along a continuum. For example, a line associated with between 30 and 40. Let us say you are talking about stream flow. Between 30 and 40, you have a line and it can assume any particular value along the line, and therefore, 30.0235 is a possible value, 30.5 is a possible value, etcetera, unlike the discrete random variables. So, the continuous random variables assume infinite number of values, whereas the discrete random variables can assume only finite or countably infinite number of values. Countably infinite in the sense you may have 0, 1, 2, 3, etcetera, but it can go up to infinity, but they are still countably infinite number of values. They are still discrete values. All right. Now, we go to the continuous random variable, much the same way as we defined for the discrete random variable. We define now what is called as a probability density function. So, any function which is non-negative, f of x greater than or equal to 0, which is non-negative, and the integral between minus infinity to plus infinity with respect to x is equal to 1. So, any function that satisfies this is a probability density function. So, we denote this as PDF, probability density function. Remember, the probability mass function gave you directly the probability, but the probability density function gives you the density, and therefore, we can talk about the probability of x taking on a certain value as the area under the density, density curve. So, let us say you are talking about this is the probability density function as an example, and on the x axis is the variable, the values that the random variable can take, and on the y axis is the PDF f of x. If you want the probability that x is less than or equal to x1, just to relate to your hydrologic variables, this may be the distribution of flows, and this may be a value of 30, let us say, and you are interested in what is the probability that the flow will be less than or equal to 30. In such a situation, you just integrate the PDF up to that point, and that will give you the probability of x being less than or equal to x1. The cumulative distribution function, which is denoted as the CDF, this is the CDF and this is the PDF, f of x is the PDF, is simply minus infinity to x, that is f of x is equal to minus infinity to x integral f of x dx. So, this gives you probability of x being less than or equal to x. So, look at this function now. This function, every point here is obtained by integration of the PDF up to that particular point. So, that is what we get as f of x, and therefore, when you go to x is equal to infinity, what happens? You are talking then about integration of integration between minus infinity to plus infinity f of x dx, which would be equal to 1, and therefore, the value approach is 1, or the maximum value as x is equal to infinity will be equal to 1. Now, from the CDF, we should be able to get the associated probabilities. Let us say that I have a value of 30 here. What does this value give? It gives the probability of x being less than or equal to 30. All right. Now, from this it is obvious that probability that x takes on a value between x1 and x2. Let us say you are talking about this region now. This is a probability density function f of x. So, to get any probabilities, you integrate the PDF over that particular region. So, probability that x takes on values between x1 and x2, you identify the region under PDF and then integrate that. So, that will be between x1 and x2 f of x dx. From this it follows that it will be equal to f of x2, which is the area up to this point. All of this area together is f of x2 minus f of x1, which is this area, and that is how you get this particular area. So, probability of x taking on values between x1 and x2 is simply f of x2 minus f of x1, and this is in fact this is f of x2 here and this is f of x1. So, this gives the probability that x takes on values between x1 and x2. So, that is the primary concept. So, in probabilistic analysis, you must remember the concept of probability mass function and the probability density function, and of course, the cumulative distribution function. So, both for discrete as well as the continuous random variables, we have the concept of cumulative distribution function. In the optimization models that we will be dealing with, we will be typically dealing with the continuous random variables, because for example, you may talk about the stream flow probability distributions or the evapotranspiration probability distributions and so on. Now, these are all continuous random variables. So, we will see some examples dealing with the continuous random variables, so that the concepts are clearly understood. Let us say that you have a PDF defined by f of x is equal to 2 e to the power minus 2 x for x greater than or equal to 0. For this now, we need to derive the CDF. First of all, make sure that this is a valid PDF. To make sure this is a valid PDF, what are the two conditions that it has to you have to check? One is that it is non-negative. So, for x greater than or equal to 0, this is non-negative, that is satisfied. The other one is that minus infinity to plus infinity f of x dx must be equal to 1. So, verify that between 0 and infinity 2 e to the power minus 2 x dx is in fact equal to 1. And as we will see later on, this is in fact the exponential distribution that we are talking about. So, for this simple f of x, which is a PDF, we will derive the CDF first, and then we will look at the probability that x lies between 1 and 2. We will also determine x such that probability of x being less than or equal to x is 0.5. We will determine the value of x such that probability of x being greater than or equal to x is equal to 0.75. So, CDF by definition is recall capital F of x is equal to integral minus infinity to plus infinity, I am sorry, minus infinity to x f of x dx, and in this case it will be 0 to x, because minus infinity to 0 the f of x is 0. Remember, whenever we define it like this, is equal to 0 elsewhere is understood always. So, this f of x will have a value of 0 elsewhere, and therefore, it turns out to be the same as integral between 0 to x f of x dx, and it is a very simple integration. You can verify this. You will get f of x is equal to 1 minus e to the power minus 2 x, and this is defined for x greater than or equal to 0. So, this is the CDF. To get the CDF, all you have to do is integrate the PDF between minus infinity to x. Then we want the probability that x lies between 1 and 2. Recall that we just defined probability of x taking on values in a particular region between x 1 and x 2 is simply f of x 2 minus f of x 1. And we have obtained the f of x already. So, in that we substitute x 2 and x 1 values. So, first we will determine f 2, which means x is equal to 2 is what we are putting here, and that turns out to be 0.982, and f of 1 we put x is equal to 1 in this, and that turns out to be 0.865, and therefore, the probability of x taking on values between 1 and 2 is simply f of 2 minus f of 1, which is 0.117. Now, you look at this example now. We want that particular value such that probability of x being less than or equal to x is equal to 0.5. Now, such problems arise in hydrology when we are talking about, let us say, the low flows, and we are interested in what is the probability that the flow will be less than or equal to a certain given value here. Especially in water quality problems, we will be interested in probability of x being less than or equal to a given value, where x is the stream flow. Now, the f of x is given. So, what we will do is, this is what probability of x being less than or equal to x is by definition simply f of x, and f of x we know is 1 minus e to the power minus 2 x is equal, and therefore, we equate it to 0.5, and from that you get x is equal to 0.35. Then we determine x such that probability of x is greater than or equal to x is equal to 0.75. Now, these kind of problems arise when we are talking about exceedance probabilities. Typically, we use 75% exceedance values and so on, where we are looking at what is the particular value of flow which is exceeded 75% of the time. So, we are talking about probability of x being greater than or equal to x is equal to 0.75. We are interested in getting the value of x. So, we write this as probability of x being greater than or equal to x as 1 minus probability of x being less than or equal to x. For this, you just refer to stochastic hydrology course. I will quickly explain this. Let us say that this is a particular value of x. What does this area give? This area gives probability of x being less than or equal to x. And what is this area? This area gives probability of x being greater than or equal to x. And the total area is 1, because minus infinity to plus infinity f of x dx is equal to 1, and therefore, the total area of the PDF is 1, and therefore, we write probability of x being greater than or equal to x as equal to 1, which is the total area, minus probability of x being less than or equal to x. And probability of x being less than or equal to x is nothing but f of x. So, that f of x is what we write here, which is 1 minus e to the power minus 2x. So, probability of x being greater than or equal to x is equal to 1 minus f of x, which is 1 minus e to the power minus 2x, and that we equate it to 0.75, which is given, and from that we get x is equal to 0.114. So, given the f of x, which is the PDF, we know now how to calculate various probabilities associated with that. Then there is the important concept of the expected value. Now, all of these we will be using subsequently in the optimization. So, I will just go through quickly the definitions of these various terms that we will be using. Now, the expected value is the first moment of the probability density function about the origin. So, you take the moment of the area about the origin, which is simply what we are doing, minus infinity to plus infinity x f of x dx. So, this is the first moment of PDF about the origin, and this is what we call as the expected value and denote it as mean mu, and it is variously called as the mean and the expected value. In fact, when we have the sample estimate of this, we call it as simple arithmetic average. We will come to that presently. Now, in the discrete case, now this is for the continuous case. In the discrete case, mu is defined as I is equal to 1 to n summation x I into p x I. So, x I is that particular value of the random variable corresponding to I is equal to 1, p x I is the probability that x is equal to x I, and I is equal to 1 to n is the sample size if you are dealing with the discrete variables. Then we have the concept of variance, which is simply the second moment of the PDF about the mean. So, first moment we took it about the origin, like that you can take second moment, third moment, etc., also about the origin, but now onwards we start taking the moments about the mean itself. So, let us say that this is the expected value of x or equal to mu, and then we start taking moments about this expected value itself. So, the second moment about the mean is in fact the variance. We denote it as sigma square, and that is expected value of x minus mu the whole square. Okay. Now, you first define the moment here first. So, the second moment about the mean is integral minus infinity to plus infinity x minus mu the whole square. We are talking about the second moment f of x dx. So, this defines the variance, and this we can also see that it is expected value of x minus mu the whole square. There is a small concept that you must know here. Expected value of g of x is equal to minus infinity to plus infinity g of x f of x dx. That means, what we are saying is expected value of a function defined on the random variable x is equal to minus infinity to plus infinity that function into the PDF with respect to x, the integration. For example, you look at this expected value of x, where the function of x is x itself. Therefore, this is x f of x dx. The expected value of x minus mu the whole square, where the function is x minus mu the whole square, is equal to g of x f of x dx. So, the variance is written as expected value of x minus mu the whole square. Now, these are called as the population moments, but typically what you will have is you will have a sample of observed values. The population is the set of all possible values of the random variable. For example, you may have a thick book consisting of 1000 pages, let us say. This and you are interested in picking up randomly certain pages. So, the page in a book is the random variable. The collection of all the pages, which is 1000 pages, is the population, and any subset of the population. For example, you may consider the pages in a chapter, in a particular chapter of that particular book, which is a subset of the population, and that is a sample. Now, in hydrology, typically what happens is that you will have observed data. Now, this observed data constitutes a sample, and therefore, the moments that we just defined, for example, the expected value, the variance and so on, we need to determine for the samples, and we now give the sample estimates of the particular moments. So, the sample estimate for the variance is denoted as S square is equal to I is equal to 1 to n is the number of observations in the sample, xi minus x bar the whole square, x bar is the arithmetic mean, and x bar is given by sigma xi over n over all I is equal to 1 to n. So, this is simply the average, arithmetic average, divided by n minus 1. We use n minus 1 instead of n because we are interested in what is called as a unbiased estimate. Now, all these details you can go to this NPTEL stochastic hydrology course. In that all these concepts are clearly are elaborately discussed. So, given the sample, then you will be able to determine S square, which is the variance. The standard deviation is defined as the positive square root of the variance. So, sigma is equal to positive square root of sigma square, and for the sample we denote it as S as plus root of S square. Then we have the concept of the coefficient of variation, because both the mean mu and the standard deviation sigma will have the units of the original random variable itself, and we want to have a unitless quantity to examine the variation, and that is why we define the coefficient of variation as sigma over mu or S over x bar. As you can see, this will be a unitless quantity. So, we have the concept of expected value of x now, we have the concept of probability density function and the probability distribution function. We have seen the concept of the mean and the standard deviation as well as coefficient of variation. Now, with this background now, we should be able to consider the probabilistic information contained in the observed data explicitly in our optimization model, which means what? If you look at your reservoir operation problem, inflow Q was specified. Now, instead of specifying Q as a deterministic value there, we may specify Q in terms of the probability distribution of Q in the optimization models, and use the probabilistic information on the stream flow in the optimization models. That is what we call as explicit stochastic optimizations. Now, when we go to probability distributions, there are a certain number of most commonly used probability distributions. For example, you use normal distribution, log normal distribution, gamma distribution and so on, exponential distribution and so on, depending on how well the data fits those particular distributions. Now, these common distributions we will quickly revise or review in the next class, but I again repeat that for all these topics on probability theory, you can refer to the stochastic hydrology course on NPTEL, where these have been discussed in more detail. So, in today's class essentially we started with the important topic of reservoir operation or reservoir systems with random inflow. So, this is the first time that we have started, we have forayed into the area of uncertainty. We are now talking about the hydrologic variables being random and not deterministic, and we have started with the concept of the probability, we have started reviewing the probability concepts. But before that I just explained what we mean by implicit stochastic optimization and explicit stochastic optimization. In the implicit stochastic optimization, you recall now that in the implicit stochastic optimization, the model itself remains deterministic, and this model you run over a large with a large number of inflow sequences, and thus you address the uncertainty, because rather than running it with one sequence, you are running with several sequences, all of which are equally likely to occur, and therefore, you will address the uncertainty associated with the inflows by considering several sequences, and therefore, you generate several sequences of output of the model. So, the model you do not touch, simply run it for different sequences. Whereas, in the explicit stochastic optimization, the model itself considers explicitly the probabilistic information contained in the inflow sequence through the probability distributions, and therefore, only one single run of the model is all that is necessary. And then we defined what is a discrete random variable, what is a continuous random variable, what is the probability mass function, probability density function. We also looked at the cumulative distribution functions, and then examined how we determine the probabilities associated with various events. And towards the end of the class, I just introduced the concept of the expected value of x and the variance. Now, all of these concepts we will be using when we go into explicit stochastic optimization. There are two classes of models that we will be talking about. One is called as a chance constrained linear programming, the other one is the stochastic dynamic programming. However, in the next lecture, we will introduce certain probability distribution functions that are commonly used in hydrology. Typically, we will start with the normal distribution, go on to log normal distribution and exponential distribution. Thank you very much for your attention.